IBM's mean Indian Bridge Management System. Post-collapse of Damanganga Bridge in 2003, research on IBM started and continued till 2015. MORTH appointed IDDC engineers to develop and implement IBMS system in June. IDDC commissioned IBMS in September 2015. Field consultants were given tablet software to capture data and upload on the IBMS. IBMS is the first fully digitized system. IBMS becomes largest database of bridges owned by single owner with data for over 172,000 structures.
IDDC Engineers is proud to present Indian Bridge Management System. Bridges help us overcome obstacles and cross them. Bridges are important to our transport and economic growth. Historically, India boasts one of the oldest bridge. NASA also confirms the reminiscence of such man-made bridge between India and Sri Lanka dating 17.5 lakh years ago. Bridge management system concept was initiated after the failure of Silver Bridge in USA in 1967, which resulted in the death of 46 people. Immediately, USA adopted National Bridge Inspection System, which formed the basis of all bridge management systems the world over. In India, our directors Sachin Joshi and Sitaram Sagi conceptualized the Indian Bridge Management System, IBMS, for Government of India, which is being implemented through Ministry of Road Transport and Highways. Large volume posed a challenge to development of the system. Database will have more than 120,000 culverts and bridges. The bridges are given a unique identity number. The precise location detail in the form of latitude and longitude is collected using the GPS. Engineering properties of the bridge design, material, age, and other technical details of the bridge are collected. The structural component rating is done, and also the socio-economic parameter rating is done. All this data is collected in real time and can be uploaded onto the server directly from the site using a handheld device. Based on the inventory and rating codes, IBMS analyzes the data and identifies bridge which need further investigation using various non-destructive testing procedures. A detailed remedial plan is then defined for each tested bridge. Ranking of the bridge for repair is driven by a logic which is based on the cost of repair, the importance of the bridge in socio-economic scenario, and the level of deterioration in conjunction with the traffic on the bridge and age of the bridge. This ensures technical and socio-economic logic to the sequence of bridge to be repaired. Every government will benefit in short term from the creation of such database of the bridges. In long term, it optimizes the use of funds available for rehabilitation of bridges. The overall efficiency, performance of the bridge, and its longevity will improve. Travelers on highways and roads will benefit due to assured connectivity. As the bridge becomes important, so will the attention being paid by the user, by the client. It will also improve due to Indian Bridge Management System. To conclude, there is no sense in losing our asset. IBMS provides a solution for bridges, which are our national asset, which justify preservation and regular maintenance. At national level, it is being implemented now. Every state government needs to ensure the last mile conductivity by implementing IBMS.
In October 2016, Honorable Minister Nitin Gadkari dedicated IBMS to the nation at the first international conference IBMS 2016. August 2017, IBMS identified over 100 bridges for immediate repair interventions as announced by Honorable Minister in the Parliament. Bridges in need for testing were also identified. 4 cycles of data was accumulated in 3 years of project's tenure. Data from 10 cycles can be used to analyze the deterioration occurring in the bridges and formulation of predictive tools and risk index. Inventory of bridges is captured with ratings for the bridge. During inspection, ratings are validated to define the cause of distress. Testing is used to confirm the cause of distress. Based on cause, repair interventions are defined. Sustained inventory, inspection, testing cycles will enable IBMs define the deterioration models and risk index.
Unified Bridge Management System, or UBMS in short, is the upgraded version of IBMS. UBMS has the following 9 modules: inventory, inspection, testing, repair, analysis, management module, which also has a risk analysis and priority functionality, administration, report module, dashboard for summary statement. All the modules of UBMS are digitized, and if required, all decision making can be implemented by UBMS. The software essentially has 2 parts. The heart of the system is the server software, which resides on the cloud server. The software which communicates with the server software is the tablet application, which resides on the tablet or mobile. Both software require login and password, without which the system cannot be operated. This tablet application provides input to the server via internet connectivity. We go to the inventory module to start collection of the data about various bridges in all the network. All inputs are in the form of alphanumeric character in the form of a string. One string is input for one parameter. Inventory requires the user to input data to create national identity number for the bridge, which creates a unique identity for the bridge in the database. Then the bridge location number is automatically picked up by the tablet application based on the latitude and longitude of the bridge location where the tablet is in use, along with date and time stamped on the input. This input is followed by a series of parameters under the admin detail, bridge geometrical detail, bridge classification number. This completes the actual observation of the bridge by the user. Subsequent to this, the user has to provide his judgment relating to the condition of the bridge by providing rating for the bridge structural rating number, bridge functional rating number, and finally the bridge socio-economic rating number. These 3 ratings are followed by submission of photographs to the bridge. 6 to 8 photographs showing inventory details are submitted to the system. Once complete input are saved on the tablet application as per requirement, the tablet application will prompt the user to submit the same to the server by uploading the same to the server. The tablet application does not communicate directly with the main server software, but via a secondary server called staging server. This facilitates the nullification of the possible attack directly on the main server software and database saved on the national server. The user working on the server end has to accept the data received from the tablet application and check for the correctness and post the same for synchronization to the database on the national server. The synchronization with the database can be done by logging onto the national server and pressing the sync button. All data posted by the staging server will now get synchronized with the database of the national server and is available for analysis and reporting. On the national server, accepting the inventory data allows the user to assign the bridge for bridge inspection if the ratings are in the range which require immediate inspection. Else, the bridge can be assigned at a later date for inspection. On assigning the bridge for inspection, the bridge will pop up on the bridge inspection module of the tablet application, which can be inspected once the user logs in as a bridge inspector on the tablet application. Data collection is essentially done with the bridge inspector being close to the bridge component in each span. Data for both structural and non-structural components of the bridge is to be collected during the bridge inspection process. The structural data is collected for 4 main components of the bridge, namely the deck, superstructure, substructure, and the foundation. For each of the component, data is essentially collected for each element in the component. For example, data is collected for each span element of the deck slab, each girder within each span for the superstructure, each pier within each span for the substructure. Similarly, elemental data is collected for each component within each span to complete the structural data collection. Then data is also collected for non-structural element in each span, like protection work, wearing coat, drainage spout, handrail, and similar elements. Once all the observations are completed, the bridge inspector has to validate the ratings assigned to the bridge component during the bridge inventory process. This validation, once complete, will automatically overwrite the rating values in the bridge inventory of the database with the inspection data is synchronized on the national server. Such validation process eliminates the risk of using wrong input during the decision-making process. During inspection, details of damage within each span is noted for each element in all four components, and measurements are noted for such damage observed. This enables evaluation of quantities essential for bill of quantities during repair estimation. During damage observation, a judgmental prognosis is created as to understanding the reason of the damage in the form of a cause matrix by assigning rating numbers to all 11 numbers of causes of damage. Furthermore, closer photographs are uploaded on the system during bridge inspection process. Ideally, the photographs for various damage indicating the extent and type of damage need to be captured with which is illustrations of the damage observed on that particular date. Comparison of such photographs enable the bridge inspector decide about the severeness of damage and its propagation speed. Inspection process is very critical in all decision-making process associated in the system and should be undertaken by a properly trained, experienced bridge inspector. Once data from the bridge inspection is saved properly on the tablet, user is prompted to upload the same to the staging server. On staging server, it is validated and then synchronized to the national servers, similar to the bridge inventory data. On the national server, the decision-making process is automatically started based on the prognosis of the cause of distress. Testing essential for confirming the prognosis is shortlisted and bridge is assigned to testing, indicating the span to be tested and the type of test to be conducted. Bridge is now assigned by the user for testing. Bridge assigned for testing pops up on the tablet application once the user logs in as a bridge testing engineer. The bridge to be tested for confirmation of the cause of distress. Such confirmation enables the system to generate proper remedial interventions essential for rectification and elimination of the cause of distress. The bill of quantities are confirmed for the type of remedial interventions and generated for implementation. The bridge is assigned for remedial intervention. Once all the bridges on the network are inspected and bridges in need of testing are tested, the subset of bridge to be provided for remedial intervention is generated by the system, and the budget calculated for providing remedial intervention is provided by the user to the system. This budget is then used by the system to generate a list of priority and ranking of bridge which should be provided remedial intervention immediately within the funds available with the department. All bridges which are not provided remedial interventions are assigned to reinspection by the system and put on observation list till the bridges are repaired and rectified. The assigned bridges for observation means that they have not been provided with remedial intervention. The budgeted amount for all such bridges is then added to project the fund essential in subsequent period of time. This process results in fund estimation for remedial action of the future. However, actual process of deterioration is dynamic and distress increases over a time when remedial interventions are delayed. This should be remembered by the user for judicious estimation of fund requirement. Analysis of all available data provides us with actual
available bridge population on the network and also the results of the subset of bridge following the same age group. Subset of bridge which have functional or structural deficiency. Similar as analysis yields subset of bridge for same type of material, design philosophy, same level of distress in need of immediate intervention. Higher this percentage, better is the efficiency of the network. Reports of all analytically evaluated subset can be printed in either PDF or hard copies of the system. The system also enables periodic report generation on the amount of bridge inventorized, inspected, tested, repaired, etc. during the period of time. Dashboard is a tool for creating the summary of a system working for very senior executives by providing pictorial views of the working of the system. It provides information on the system using Excel sheet dump data extracted from the database of the system and then generated automatically the pie charts or graph for various functionalities of the system. To summarize, it is not prudent to allow our bridges to deteriorate, resulting in collapse and loss of innocent life when cost-effective tools like UBMS are available.
In March 2016, Honorable PM Modi talked about the significance of IBMS when Setu Bharatam was launched.
Our Honorable Prime Minister Sri Narendra Modi and our Honorable Minister for Road Transport and Highway, Ms. Sri Nitin Gadkari, both have mentioned about the importance of the system on 4th March 2016 during the launch of Setu Bharatam.
डिपार्टमेंट में इस बात का पता ही नहीं कि हमारे देश में ब्रिजेस कितने हैं और इसलिए हमने एक कंसल्टेंसी को अपॉइंट करके हमने देश के पूरे ब्रिजेस का डाटा तैयार किया है और ये डाटा तैयार करके ब्रिज का भी जैसे व्यक्ति का बायोडाटा होता है वैसे ब्रिज का बायोडाटा होगा ताकि कब तक उसका लाइफ है क्या है सब उसका डिटेल होगा और उसके मरम्मत के लिए भी हम स्पेशली जो सुशिक्षित बेरोजगार अभियंता है जो सिविल इंजीनियर है इनको काम देकर मेंटेन करने की भी कोशिश करने की योजना तैयार कर रहे हैं। अभी नितिन जी बता रहे थे आपको भी आश्चर्य होगा कि इतनी बड़ी सरकार उसको एड्रेस मालूम नहीं है कि कौन सा ब्रिज कहाँ है, यानी कैसे काम किए होंगे। और मैं इसमें कोई इलेक्टेड बॉडी का दोष नहीं देता हूं, फलाने प्रधानमंत्री थे या ढिकले राज्य मंत्री थे, मैं ये नहीं कह रहा हूं। व्यवस्था का दोष है ये, हमने इन चीजों को प्राथमिकता नहीं दी और इसलिए सबसे पहला काम किया कि भाई एक बार देखो तो सही इस देश में क्या है, कहां है, क्या स्थिति है। अब उसका ग्रेडेशन का काम चल रहा है कि उम्र के हिसाब से ब्रिज किस कैटेगरी में आते हैं, लंबाई चौड़ाई के हिसाब से किस कैटेगरी में आते हैं, मटेरियल के संदर्भ में किस प्रकार की डिजाइन है, कितनी पुराने जमाने की डिजाइन है, नई डिजाइन, सारा उसका ग्रेडेशन चल रहा है। और दूसरा उसका एड्रेस पक्का हो रहा है लॉन्गिट्यूड लैटिट्यूड के माध्यम से स्पेस टेक्नोलॉजी का उपयोग करके कहां यहां ये ब्रिज है। हो सकता है कुछ जगह पे कागज पे ब्रिज होगा, वहां नहीं होगा, वो भी हाथ में आएगा।
Honorable Minister Nitin Gadkari's envisioned use of UAV to reach the bridge to report distress. UAV will upload videos directly to IBMs which will use artificial intelligence to classify the distress and define cause of distress. Requisition of the required type of testing is conducted by robotic tools. IBMS defines the repair intervention essential. This entire process can happen remotely by deploying AI. This can be achieved with the active cooperation of the research team and ministry in years to come. BMME Federations is established to cater to training and continued research to achieve complete vision of the minister.
Unified Bridge Management System understands that research has to be continued and the research team is geared to take the challenges and face it head on. However, we understand that the path is long and will need focus of our team. Bridge management system all over the world are moving to digitization of the structural system. The location of the distress is captured in GPS coordinates. IABSC has constituted a high-powered task group TG 5.6 under the chairship of Vanya Samak, specially to focus on linking four-dimensional BIM to BMS. Our Mr. Joshi is a part of this task group. Similarly, Mr. Joshi has been associated with Cost Action Europe Group in formulation of important documents for Unified Bridge Management System. Structural health monitoring using various upcoming technologies are being used to monitor elements of the bridge. This technology has moved from a wire-based system to highly dependent on internet and cloud-based system. Wireless sensors are extensively used to monitor structure. These sensors can communicate directly with the server, or if required, they can communicate with the server via an internet data logger. This makes it easy for adaptation to bridge management system. Race to fully automated system using artificial intelligence to monitor the bridge is already on. Bridge inspection using unmanned aerial vehicle, which are remotely activated based on the need to inspect a bridge and capture the distress zone. Thereon, analysis of this observation using artificial intelligence to decide the testing essential is done by robotic tools of testing, which results evaluation done using inbuilt computer interface and transmitting the result back to BMS server. All form a part of this race to convert a human controlled bridge management to automated bridge management. Use of drones and UAV is proposed to be adopted for automated collection of data. With the advent of GPS in BMS, it is easy to focus on an element of the bridge showing distress and capturing pictures of these elements only. Closer view and digital zooming facility make it an important tool for adaptation. UAV can move under the bridge deck and focus on individual elements and capture details of each element and also the overall arrangements of the bridge. Zooming makes it possible to focus on bearings and parts of the bridge which are normally not visible. Use of photogrammetric tool make it feasible to measure the quality and quantify the distress also. UBMS is a very important platform in the world of bridge management. Our research team is geared to take the needs and challenges head on.